So the fiber optic cables work on the concept of bending of light ray. So if you have two materials, one dense and one less dense. So in this case, this is the dense material and this is the less dense material. If you have a source of light and this angle of you shine it at this angle, then when it reaches the boundary between the two materials, the less dense and the more dense, we have some criteria that determines if this light will go outside or stay inside. So we have this angle. If this angle is less than the critical angle, reflection critical angle, then the light will go outside, will not stay inside. But if it's critical angle, or you see the light will go this way, you see. My pen does not work, I don't know. So if it's less than the critical angle, then the light will go outside, will cross the boundary. If it's equal, then it will be like this. But if it's more than the critical angle, then it will be reflected. This is called internal reflection. Internal reflection will happen, or total internal reflection. The light is reflected like a mirror. So if this angle is more than the critical angle, this critical angle depends on the density of these two materials. So for each material you have different angle. So if this angle is greater than the critical angle, the light, when it gets to the boundary, say this is fiber material, this is another fiber material which is less dense. So what happens is that the light is totally reflected back. So it will go and go to the other, so it will continue this way. This is called total internal reflection. Actually, fiber is glass. Fiber cable is glass constructed using two different density glass material. So the inside and outside, they are both glass, the core and cladding, but the density is different, so that this effect can happen. Because if they are not different, then this effect will not happen. Okay, so we need to have them in different densities. We'll have a laser diode, for example, or an LED that converts the electrical signal to a light signal. This light signal is will enter the fiber. Then, because if the angle, this angle is more than the critical angle, then it will be reflected and so on. So you go until you go to the receiver. The receiver is like a photodiode. It will convert the photo or the light signal into electrical signal again. So this is the concept of operation of fiber optic cables. We have light that travels, is bounded by this cable. So it's like trapping the light inside this core. Okay, it's like a you studied waveguides, so this is like a light guide. So even if you bend the cable, this doesn't mean that the cable should be straight. Even if it's bent, the light is still trapped. So the light goes actually in straight line, but because of these reflections, so it can't go even cross corners. So when you shine the light, it will go like this, because of this total internal reflection. Okay, so this is how fiber optic cables work. When this light propagates, we have different modes of propagation. As you studied in waveguides, we also have propagation modes. So in light also we have propagation mode. We have the single mode and multi-mode, the main two modes. The multi-mode is also subdivided into step index and graded index. We study this in the next slide. So this is a multi-mode step index. Step index means the densities of the cable will change suddenly, step. So this is one density, this is another density. Okay? They don't change gradually. This is called a step index. So the light will be reflected, okay, when it reaches a boundary. This is multi-mode. You see, there are different rays of light. So one goes this way, one goes this way, one goes this way. We call it multi-mode. We have another type of multi-mode called it graded index. You see, the density here does not change suddenly. It changes gradually. So when you send light, it will not reflect suddenly. It will step by step be, so it will be more like curved than this case. This is called multi-mode graded index. Of course, we have multi-beams here also. You see, this one goes this one, maybe another one goes different. So this is called multi-mode again. We have the also single mode. Single mode, normally this core would be much smaller in diameter than the multi-mode core. Again, we have core and cladding, but in multi-mode, we have only one beam of light that's not reflected like this. It will travel through the fiber. So in multi-mode, actually, we'll see the specification later. The construction of the cable is like this. So you have glass. You see there are also two. You can't, if you look carefully, you can't recognize the difference in densities. So we have the core and the cladding. They are both glass. So if this actually fiber is very thin actually, in millimeters. We'll show you some in the lab when we go back to labs. So this is not like a coaxial cable, two parts that combine to make this. It's just a glass, but it's, when it's constructed, the density of this is different from the density of the cladding. Therefore, this can trap the light inside. So we have to protect this this glass because it can, of course, be damaged if it's. So normally you'll have some Kevlar or some steel or some different types of protection depending on the usage of the cable. For example, if you see under sea cables, they are very, very well protected. Okay, so this is the glass, this is a plastic buffer. You have Kevlar normally to strengthen the cable so that you cannot stretch it and break the fiber inside, and there is an outer jacket to protect the cable. We have different types, as we said. Normally, this is, you see, single mode. Okay, so single mode normally will be thinner than multi-mode. Multi-mode, you see, this is a core diameter in micrometers, and this is the cladding. You see these numbers, core to cladding. So core is 50, cladding is 125. But here core is 7, so in multi-mode the core is very thin. They're all same cladding in this case, 125. But in multi-mode, this one will go bigger, the core. We have different specifications and different. Normally, these are the types widely used. So if you look at a single mode cable, this is the glass, the core, normally up to 9 micrometers. This is the cladding. Cladding is, as we said, 125 micrometers. And we have the protection, which is a polymer coating. So this is the light that passes through this. In multi-mode, the core would be normally bigger, say 50, 62, as we said in this table. 50, 62, these are the common ones used. And the cladding is again same, so this diameter is same for both. And there you have the plastic or the cover. You need to terminate, of course, fiber optic cables again, like coaxial cables, like Ethernet cables. So how you terminate them? You use different kinds of connectors or terminators. So we have straight tip. You don't need to remember these, just ST, we call them ST connectors. So ST, they were used in the past, but nowadays we don't use them that much. ST connectors, okay. So this is the fiber, look. No, actually it's not the fiber, this is the buffer material which is connected. The fiber will be inserted here. We'll show you maybe how to do some of these also. Although you need some special tools, but you know the concept at least. Subscriber connector, nowadays these are used most widely in LAN and WAN with multi-mode and single mode. So we use these both for multi-mode and single mode. This is actually glass, but it's not the glass or the fiber from the cable, because here the connection will happen here. You have to properly terminate these. We have the LC connectors, Lucent connector. It's company, Lucent Communication Company. You just need to remember the names. LC is almost same as SC, but it's smaller in size. Okay, so it's also widely used. And we have the duplex LC. So the duplex, this is one cable. Normally we have one for sending, one for receiving. So In this case, it's called duplex because it has the sending and receiving together. This So we are talking about connectors. So we need to connect the cable when we have, for example, to terminate or to connect it to a switch or whatever device. So we need these connectors. We talked about the SC and LC, SC and ST and LC and duplex LC connectors. The duplex will have both the sender and receiver connector. If you look at the performance of the fiber optic, although we are dealing with light here, but still, because this glass, the glass is not pure glass, there is also attenuation in this case. So when the cable length increases, of course the loss will increase. The loss is also affected by the wavelength. So the wavelength of the light, nanometers, you see, here the attenuation is low, here it's very high. So you have to know which wavelength you use. Here it's low. So depending on the wavelength of the light, the attenuation in the cable or the loss will also change. So here is lowest loss, here is the highest loss. dB per kilometer here. So at this frequency, for example, the loss is very low, it's less than, say, 0.5 dB per kilometer. So we'll see some advantages and disadvantages of the fiber optic cables. The obvious advantage is actually the bandwidth. Actually, there is no limit on the bandwidth that the fiber optics can offer. Only the technology limits the bandwidth. So it can go to 100 up to maybe 100 gigabit per second data rates. So the limitation are not the fiber but the technology. So because when you as we said, send the light or receive the light, these are devices. These devices can operate at frequencies, specific frequencies. So these are the bottlenecks. This media can carry almost unlimited data rates, but these are the bottlenecks. So we have to improve these converters to get higher data rates. The attenuation is, of course, less. So a signal can run for 50 kilometers, actually up to 1,000 kilometers without requiring regeneration or repeater. Okay, but for a coaxial, for example, you need repeater every 5 kilometers. For UTP, for example, you need repeater for when you go up to 100 meters, then you need a repeater. So you see the UTP, the coaxial, so if you want to make a connection with another city, obviously you are not going to use UTP or coaxial, you go to use fiber cable. So if you have a connection between two continents, for example, undersea cables, and the distances can be thousands of kilometers, of course the only option is fiber cable, because attenuation is low. You need less repeaters, because this is, if you need many repeaters, then it will be very costly and hard to maintain. The advantage is immunity to electromagnetic interference. So why, I'll ask this question, why the fiber is immune to electromagnetic interference? Should be
Dikkat çünkü light'ti da der bazı nefsi kern.
Very good. So it's because it's light. It's not. We are not using electrical signals. Only at the ends, when we use converters, we'll use the electric. But in the cable itself, it's a light signal which is not affected by interference, electromagnetic interference. This is very big advantage, of course. When you have noisy environment, then it will not be affected by electromagnetic. And of course it's glass, so it can of course resist corrosion. It's glass, it's not like copper or steel that will corrode with time, or so it's very resistant to corrosion, can last for many years. And weight, because this fiber is only it's very thin in millimeters. You see, the weight is light. Of course, when you go, for example, cables that need protection, we have Kevlar, we have steel reinforcement, so it can increase the weight of the cable, but the fiber itself is very light. It's even lighter than UTP or coaxial cable. And the other advantage is security. Because it's light, so you cannot tap the cable. Fiber optic cables are more immune to tapping than copper, create antenna effect. So if you have UTP, for example, and someone wants to listen to the signal, he can attach a loop, for example, to the around the cable, and he can catch some of these signals and amplify them, filter them. He can listen. Or of course this is a very important concern if you are concerned about the security of your data. But if it's a fiber, no one can listen to these signals because it's light. How you can tap it? How you can, unless you cut the fiber and connect it again and add some thing to, but in that case you'll notice, because there will be disruption in the service, so you'll notice that. So it's more immune to security breaches than copper cables. Please send me your names in the chat so that I save it. Now I'll let you think of some disadvantages. What are the disadvantages? Can you tell me any disadvantage of fiber?
سيد السعر میگیرنه؟
Well, that can be true to some extent. It's more expensive than UTP cable, of course. The other thing is installation. So you learn, we'll teach you how to do the UTP cables, but to do the terminations and to install the fiber cable, you need more training actually, and you need some equipment that are not that cheap. So its installation and maintenance is harder than a normal UTP cable or STP or coaxial cables. And actually you need training and some skills to do that. The light is unidirectional, so you have a cable for normally for sending, and you need another cable for receiving. So in copper you can do both. As I said, you can use duplex, so you can send and receive at the same time. But that's not a great limitation, because you can have two fibers, one for sending, one for receiving. That's normally what we do. And the cost, as I said, the cost and interfaces are relatively more expensive than other guided media. But of course, when you think about the bandwidth at this, for example, you have two lines, okay, and there is lots of traffic. So you need, for example, 100 gigabit per second. So even if the distances are small, UTP cannot go to this data rate. It's hard actually. So the convenient option would be using fiber cables when the distances are very high. So for example 100 kilometers. It's not logical to use cable, coaxial or UTP or STP for these distances. So you'll go for fiber cables. So it'll provide you less attenuation, higher data rates, but more costly, of course. So you have this disadvantage, the cost. If you look at here this table, the bandwidth in UTP cable, nowadays we can go up to 10 gigabit per second with UTP, but with fiber you can go to up to 100 gigabit per second with the available technology. Of course, as we said, the limit is not the media, but here mostly the limit is media with UTP. The distance, you need mostly, as we said, for UTP, you need a repeater every 100 meter. But the fiber can go up to 100 kilometer. If it's a single mode, it can go up to 100 kilometer without a repeater. Of course, as we said, the UTP is not immune to EMI and RFI, electromagnetic interference and radio frequency interference. But the fiber is almost, is completely immune actually, unless you go just terminals. Immunity to electrical hazards, because this is copper, so it can conduct electricity. The fiber is glass, which is insulator, so it's not, it will not conduct electricity, so it's immune to electrical hazards. Actually, of course, the cables will contain sometimes steel reinforcement to especially intercontinent cables. So still they may be hazardous when there's electrical current or media and connector costs. These cables, we need the RJ45 connectors, which are cheap and readily available. But the connectors, the ones that we've seen, the SC, LC, these connectors are cost more, and you need to do them properly, of course. Safety precautions. Here you need to be careful when you do these because it's glass, so you have to wear gloves, or because they can, of course, shatter and go and do injuries, or of course you know. So that was about guided media. Now we study the unguided. Unguided means there is no specific path between the source and destination. So this is a wireless signal. It can travel in direct line of sight, but it can go to the atmosphere, go back, for example. So there is no specific, or even if there is no air, this signal can still travel in the free space. So therefore we call this unguided media. So mainly we have electromagnetic waves. These waves can be infrared or can be wireless signals. Normally we'll have radio waves or microwaves or infrared light, or sometimes we use lasers. Lasers mostly in the infrared range, so you can send the signal. In this case, why we call it unguided? Because you don't need any media, even free space will work. Okay, so if you send the laser from this point to this point, there is no need for a media to transmit. You can transmit it through the air, through the space. Okay, so it's called unguided media. We have a wide electromagnetic spectrum, as you know. The range from 3 kilohertz to 300 gigahertz is for radio wave and microwave. Then you have the infrared, and then you have the light, and then the UV, and so on. So this is a wide range of frequencies in the spectrum that we can use for unguided communication. Propagation can be, as we said, line of sight, or it can go sometimes to ionosphere. So depending on the frequency, so these frequencies, for example, can go to the ionosphere, be reflected back, and this is not a line of sight communication. Above 30 megahertz, you need line of sight for radio. They will not be reflected at the ionosphere layer. We also have ground propagation. If at very low frequencies, the waves can propagate along the surface of the earth. So you don't need here also line of sight, but you need to have low frequencies, very low frequencies. We have these bands. You don't need to remember them all, but just know the names. Very low frequency. We have low frequency. We have medium frequency. This is, you know, the radio frequency, AM radio. We have the high frequency. We have the VHF, which is used in FM radio, 30 to 300 megahertz. We have the UHF used in TV, UHF TV. We have the super high frequency. Of course, they are all, you see here, you need line of sight. As I said, when the frequency is between this, you can use the sky waves. or you see the ionosphere reflection. When the frequency is low, you see it's less than 2 megahertz, the propagation is mainly ground waves, ground propagation. Okay, so these are the bands. So as we said, wireless transmission can be radio waves, microwaves, and infrared, or even visible light. We have different sorts of antennas for radio signals. We have omnidirectional. Meaning of omnidirectional is propagation pattern is symmetrical around the, so it's like this. So if you are here, if the distance is same, so you receive the same amount of signal, or if you are here. So in the same circle around it, if this is the center, the signal will be always the same. This is called omnidirectional. So the pattern will be, or the signal will be the same when you are at the same distance from the antenna, even if you are any. Of course, we are speaking about this plane, not the vertical plane, the horizontal plane. It can be, because normally they'll have loops like this. You've studied propagation, so the signal here will not be the same as the signal here, even this. We are speaking about the horizontal plane. We have also directional antenna, unidirectional. You see, like dishes, they focus the beam into a single direction. Like this is a horn antenna. So these are directional antennas. They add some gain to your signal, and depends on the size and shape of these antennas. Radio waves are used normally for multicast communications, such as radio and television, and paging system. So you have multicast means there is one sender and many receivers. Normally in multicast is unidirectional. You send and the others will receive. Microwaves are used for unicast. Unicast means point to point, like send and receive communication, such as cellular telephones, satellite networks, and wireless LANs. So we use normally what frequency, who can tell me? We use most widely in wireless LANs, Wi-Fi. What's the frequency?
2.4 gigahertz.
Yeah, that's the most common frequency, but nowadays we have another frequency that's used for higher frequency rates. We'll study this in more detail when we study the LAN technologies. We have other frequency, which is 5 gigahertz, which is used at higher data rates. Infrared signals can be used for short-range communication in closed area using line of sight. Of course, they are light, so you need line of sight communication. So infrared cannot travel through walls, of course. You have to have clear, but wireless signals, even they can propagate through obstacles, but you need higher power, of course. So that's it about today's lecture. I'll just stop recording and let you